let us now consider a very specific effect that happens for a spin qubit and becomes a very quick and important reason why you need fine-tuning when you operate your qubits. And that's the Overhauser field estimation. So when you fabricate your qubits, ideally you think about them, okay, so I have my quantum dots, there is some spins, and I am manipulating those. However, as we discussed previously, these qubits, they always sit in some solid state lattice. And for a lot of quantum dot materials, there is a non-zero nuclear spin of the material. And then what happens is that your nuclear spin can couple to the electronic spin. This gives rise to the effective field that can have an influence on your qubit frequency. Here on the right, you have an example from a paper from 2017 where they really rigorously studied the effect of this Overhauser fields on the singlet triplet qubits in double quantum dot. Specifically, what happens for pedagogical purposes today can be described by this super simplified Hamiltonian. And if you want to know the full truth, go read this Physical Review Letters paper. We will also give it to you in a recommended reading. But for now, let's pretend that this is it. You have a Hamiltonian that has some phase of 2 pi. Then you have a sigma z term. And then you have some prefactor in front of it. This is called Overhauser field gradient, and basically what it does is to make your states precess around this red axis that you see in a figure here. The frequency of that precession is given by this term, and basically if you know what the frequency of the precession is, then you can just figure out what is your state at a given time and just target your qubit correctly. If you wouldn't know this precession exists, you would have really hard time targeting the state that you want to experimentally target. What they do in this paper is the experiments that look something like this. They start from a singlet state here, and then they run a Ramsey experiment. And then here you have two axes. This vertical one is the axis of the time of the precession of the state, and a horizontal one is a lap time. So basically each column in this data is one Ramsey experiment, the precession of your qubit, and then you have a time dependence in the lap time on a horizontal axis. And you see that there is some structure in this data. Specifically, the most important, physically interesting, but control qubit super problematic thing to notice is that this frequency, this prefactor for your sigma z term is actually time dependent. So for each of your run of your experiments, you will infer a different frequency. So this is something that is really unpleasant. So not only you have this extra precession of your states that you have to worry about, you cannot just find it and compensate for it constantly in all of your operations. You need to find it and keep finding it and finding it and finding it because it changes as a function of time. We are not going to go into the physics origin of this, but it's basically another consequence of this complex solid state emergent effects that happens whenever you are operating a solid state qubit. So now let us see if we can view this Overhauser field estimation as a Hamiltonian learning task. So what we said is that each column in this data is one Ramsey experiment. And then by fitting or another method, you can infer your Overhauser field gradient. So you measure column of data, you infer your field, you measure the next column of data, you infer your field, and so on and so forth. Again, the difficult part here is that each data column is going to have a different Overhauser field because it keeps fluctuating as a function of time. But this also gives us a really simple way to extract machine learning like training set, right? Because I can take these columns, they come with a label. So instead of doing some other method of inference, we can formulate it as a task for a neural network. I measure my column of data that I get from the Ramsey. I feed it that data as an input to the neural network, and I ask the network to predict the corresponding Overhauser field. This is exactly what you are going to do in your code demo exercise with Jin. We use the master equation formalism to generate for you a fake measurements. Again, precession time on the y-axis, lap time on a x-axis. Red rectangle is shifting through the data, and you are gonna feed that into the fully connected neural network and predict your Overhauser field. So now you see that conceptually this is exactly similar to all the tasks we did previously, because from the coding point of view, this should be a piece of cake at this point. You have written all of these codes for a supervised learning before, so your actual neural network wouldn't be that different, except now you even have a one-dimensional input of your data, so that's even simpler. The really hard thing here is conceptual, because you are mapping on the Hamiltonian, you are mapping on an underlying physics, and that's maybe sometimes a little bit harder to think about. But when you train this thing using exactly the same methodology you used in the previous module, you are going to get your Overhauser fields as a function of lap time, and you can compare to the true values, and you see that a supervised neural network just like learns it super precisely, and this is exactly the plot that you are going to reproduce for yourself in the next part of this module. Let me conclude this part with sort of outlook or extra challenge for those of you who are interested. If you think about this for a little bit, you will realize that we are cheating a bit, because if I'm an experimentalist and I learn to predict the Overhauser field gradient in the experiment I just did, by the time I know it, probably things have changed a little bit already, and there is a new Overhauser field gradient, right? This time dependence was really the key thing that we were worried about. So now, what I would actually want to know is, if I know the Overhauser field at the time t, what is the one in the future, so I can sort of preemptively compensate for whatever is going to happen. So this is the real super interesting task here, and basically you learned almost already to do it. It's just that you need a slightly different neural network architecture. These are called recurrent neural networks, and if you feel up to it, pull up that recurrent PyTorch module and see if you can also implement the prediction. It's a slightly different architecture, but the spirit of the exercise is very similar. Jin is going to give you a little bit more ideas on how to do it if you would like.